not mistaken, that's me back to you there. So firstly, again, thank you. I hope it's okay for you. It's a long day, but we hope to get through 4 sessions, 2 this morning and 2 more this afternoon, to fill these gaps or these holes in the knowledge you already have, just to remind you of some of the stuff you already know, and then also to maybe refresh or to fill in a gap on some place you weren't be too sure of before. I'd like to thank my colleagues John, who's been helping me when I've gone silent for a while, and thank you for your patience. I'd like to thank Sinead, who is in as our school's liaison manager, and also to thank Rob in the background, who's helping me curate all of those comments and questions that are coming in on the YouTube channel. It's really helpful to see them. I think I've answered the questions in relation to this morning's ones. There was just one there about the acceleration. Acceleration was -10 because of the direction of travel. It was coming downwards to the Earth. It is of size 10. Acceleration is 10. Or for those from physics might know it as 9.81. But really in terms of its direction, that's why we had the minus there. So hopefully that answers your question, Kate. Okay. So now we're going to start on a new topic called trigonometry, or Trigonometry agus Illunucha. This is a lovely topic. It's one where we're going to have another set of toolboxes for us. It comes up every single year. There's different types of triangles, those that are right angle triangles and those that are not right angle triangles, the general ones. And really the way it works is it's sort of strange in that it's like a Sudoku puzzle, if you ever play with that. They give you some of the numbers, but not all of them, and you have to fill in the missing ones that are there. So if it's a triangle and there's 3 angles, they won't give you the 3, they'll give you 2 of them. Or if there's 3 sides, they won't give you all of them. They'll give you some of the angles and some of the sides, and our job is to fill them in. So really we're on a journey now for the next hour or so to fill in a few questions on trigonometry, triangles and angles. So Triantán agus Illunucha. So we're going to start with our first set of toolboxes. This is our electrician set or our plumber set or whatever, painter set. We're not going to go anywhere without these. So a definition is a triangle is a figure bounded by 3 sides, 3 taobhna, and it applies to all triangles that A plus B plus C, the 3 angles, add to 180. And there's another rule that we don't often think about, and that is that no one side can be bigger than the other 2. So imagine if you had a nice triangle, or you were trying to create a triangle, and this was one of the sides, and this was the other, and this was the other. Well, sides B and C wouldn't be big enough to join, so it really wouldn't be a triangle. So B and C have to be at least big enough to actually create 3 sides. So that's all that third one there is, that A has to be less than, no side can be bigger than the other 2. And those moduluses say there's the Jarivluach, or the length of the sides A, B, and C. So that's our toolkit. We're going to keep that. It's very important. We're going to mark that as a special page, that we keep as a slide. It's in the textbooks, it's in the log tables. We're going to keep that and leave that there. Now, just an equilateral triangle, Triantán Cóhlasach, where all the sides are the same, A, B, and C. We show that with the double dashes there, 60, 60, and 60. That's a Triantán Cóhlasach. Here we've got a Triantán, here we've got here an isosceles triangle where 2 of them are the same. And we're talking about A, and C are the same, and the 2 angles here are the same. Note that if 2 sides are the same, and the third one isn't, that the angle opposite the sides are the same. So we talk about if that's A, that's the angle A, that's C, that's the angle C. So that's what that is there. So a scalene or an oblique triangle, here we've got the typical triangle, just Gnóthríontán, where this side is different from this, and the 3 angles are different again. Really important, each lettered side is opposite the same lettered angle. So you can draw a triangle any way you like. You can call A, B, and C anything you like. So you create a triangle in your own preferred way, and you say, I'm going to call that A, I'm going to call that B, and call that C. But once you do, this must be angle C. This must be angle B, and this must be angle A. You can't just come in and write A, B, and C as three angles or three sides and then make up the angles separately. None of the equations will work if you do that. So the side must be opposite its own lettered angle. It's really important. So each lettered side is opposite the same lettered angle. This is 3 Dronilloch. This is a 90 degree. You've got the Dronilla there, the angle at the bottom there, the 90. And A, B, and C. And same again, A is opposite A, C opposite C, and B opposite B. The one thing that's special about this is the 90 degree is that this side will be the longest side. It'll be the longest side because this is the biggest angle, because there's only 90 left to share if 90 is already gone. So that'll be the longest side, and that's called the hypotenuse or the tevagon. Okay, so that's what we call that. Again, each lettered side is opposite the same lettered angle. So this is a triangle with acute angles. They're all less than 90 degrees. And this is where some of the angles, one of the angles is more than 90, an obtuse angle. Okay. There's a theorem as well, one or two, not many, but one or two theorems that we draw on from a different part of the course, and it's really about angles. And what they're saying there is that if you've got a triangle A, B, and C, that this angle here, C, plus the angle beside it is the angle on the line. So that must each add to 180. Similarly, this angle here adds to 180. And if you were to extend this one back, you'd find that that angle there, whatever that angle would be, let's call it F, that would be 180. But if A, B, and C add up to 180, and B and E add up to 180, then we can do something smart with those two equations. So let's just take those two equations. We'll say that A, B, and C equals 180, but B and E must equal 180 as well. Well, let's imagine that the B is obviously equal. So I'm just going to put B on this side. With the second equation, I can say B is equal to 180 minus E. In this one, I could say B is equal to 180 minus A minus C. It looks like they must be the same. E must be the same as A and C. Or let's look at it here. I'll rearrange the first one again. And instead of A plus B plus C, I'll say B plus A plus C is 180. And B plus E is 180. Well, if this is true and this is true, this must be the same as this. Because the 180s are equal, the B's are equal, E must be the same as A plus C. And visually what that's saying is the angle outside the triangle here, this one E, is the same as the two other ones inside. Because this plus the two inside is 180, and this plus this is 180. So this is 180 and this is 180. That's common. E must be the same as A and C. So E is the same as A and C. Similarly, if we went for this one here, C and D is 180, but C and A and B is 180. C and D 180, C and A and B 180, A and B must be equal to D. So the external angle must be the same as the two other internal angles. So that's that. That's the end of that topic. What we have on the maths.griffith.ie site is that we have all of the resources for all of the various sessions on the maths course. So the way we've broken it down is when you see this rectangular piece here called trigonometry, or any other rectangular piece with no maths on it, just a title, that means that a video starts at that space. So if you want to go back and just look up this one about sine, cos and tan with trigonometric functions, you just click on that video or move in that video to the part you want to find, the bit that you might have missed or the bit you want to look at again, because you'll know all the rest. So that's the trigonometry there. We're going to do this topic now. So we're going to start now with right angle triangles. For the next while, we're looking at just triangles that have 90 degrees. And there's loads of rules for them. And there's different rules for those that don't have 90 degrees. So here we've got a right angle triangle. We've got the 90 degree. We've got the hypotenuse, or the Pythagoras, the one that's opposite. And we've got A, B, and C. Again, note that the side B is opposite the angle B. C, angle, opposite side C, and A, opposite angle A. Each lettered side is opposite the same length. So that's really important. Now, we have this rule as well. It's in the log table. It's another one of our toolboxes. So we'll have to keep this with us as well. This is our toolbox going in to do this job. Sine, cos, and tan. Sine is opposite over hypotenuse. Cos is adjacent over hypotenuse, etc. Or sheen is or corach or Pythagoras, and all those. So you've learnt those, they're in the book. But really what we're saying is that if I want to find the sine of A, I look at the one opposite, and I say opposite and hypotenuse. So opposite over hypotenuse is the sine of this angle here. So sheen A, shin, or corach or Pythagoras. So that's the one you want. So opposite over hypotenuse. And that's the way it's done. That's an American book. Some old hag cracked all her teeth on asparagus. Oh, heck, another hour of algebra. I don't think any of those are really used, but you have your way of sheen, cos, and tan, sine, cos, and tan, and you know how to remember them. For now, this is in the maths tables book. We know we can find them. We can always refer to it. So we leave that as an important one to come back to. So now let's start with sine, cos, and tan. So here's the question. Considering angle A, you're given this triangle and you're asked to calculate angle A. Find angle A. Now, I want you to do something that you're not used to doing, or maybe it's not part of your pattern, but I really want you to think about this when it comes to triangles, right angle triangles. When you're interested in an angle, angle A, considering angle A, the first thing you do is you go to A and you draw an arrow, opposite. And that becomes the opposite, because it's opposite to the one you're interested in. So now you've got opposite. You know that this is a 90 degree. If that's a 90 degree, this must be the hypotenuse. That must be the Pythagoras. It must be the hypotenuse. And if the hypotenuse and the opposite are gone, well, there's only one left, and that must be the adjacent. So now you've named those completely: opposite, hypotenuse, and adjacent. Now, considering angle A, find sine of A. Sine of A, you say, oh, remind me, what was that? Sine is opposite over hypotenuse. Opposite over hypotenuse, opposite over hypotenuse, sine must be A over C. What's cos of A? Cos of A, well then, cos of A, we're told, is adjacent over hypotenuse. That's the congrach or the Pythagoras. So you look at the cos A and you say, there's the adjacent and there's the hypotenuse, because that's what I'm meant to be looking for. I'm meant to be looking at adjacent over hypotenuse. That's what the log tables say. So adjacent over hypotenuse must be A over, or B over C, and that's cos. The last one is tan. What's tan A? Don't know. The tables say tan is opposite over adjacent. Opposite over adjacent, that's opposite, okay, or corach or congrach. Opposite A over B, that's A over B, that's tan. So that's really important that you draw that arrow. So that's the way we get the sine, cos, and tan. The reason it's important to draw the arrow is like this. you get this triangle, the second triangle in the exam. And instead of them doing it the nice way, because you're used to doing it this way, where this is the angle, or let's say you like this one the best, where this is the angle here, you're looking at theta. They give you this question in the exam and they turn it upside down for you. And they say, no, we're interested in this angle. And you say, oh, how do I do that? Do I turn it around and then it's still on the wrong side, or what do I do with it? I don't know. So you're lucky because you have the 90 degree there, but how do you do it? Well, the way I do it is I say, considering angle B. Angle B is here. First thing I do is draw this arrow, and then that makes that the opposite. So that is opposite. Because this is 90 degrees, the one facing it must be the hypotenuse, because that's the largest one. And if the opposite and the hypotenuse are gone, this must be the adjacent. So on Tavagon, on Urkorok, and on Kongorok. So there are the three. So you have to, if you draw the arrow and you make the opposite, the rest sort of make sense of themselves. So now it says, what's sine B? Sine B is, well, again, you go back to the toolbox and you say sine B is opposite over hypotenuse. Well, the opposite is now B over C. And likewise, what's cos B? Well, cos B is adjacent over hypotenuse. So adjacent is here, that's A over C. And what's tan B? Opposite over adjacent, B over A. So that's what that's done. So this will work for any triangle every time. Remember, the hypotenuse is always opposite the right angle. The angle of interest, draw the line to it and call that the opposite. And then everything else works out. Remember always that A is opposite A, C opposite C, and B opposite B. And then you're ready to go really for all these questions. So that's that section done. We're now going to look at inverse functions. These are inverse sine, inverse cos, and inverse tan. Sin inversa, cos inversa, tan inversa. Okay? So how do we manage these inverse functions? Okay? Now, sine and inverse sine are related. We're really lucky. They're like the plus and minus. One gets rid of the other. So you can get rid of a sine by having an inverse sine. So if you had sine of theta equals, say, 0.5, you can say inverse sine of this is inverse sine this. And then you just end up with the theta. The inverse sine would cancel the sine. And you're just left with that. Or if somebody said inverse sine of, let's say, inverse sine of theta was, let me see, inverse sine of theta was 30. How do you find theta? Well, you just get the sine and the sine, and you do it that way. Theta is equal to. So that's how you can delete these. So let's see how that works. Sine and inverse, sine theta is 5 over 13 in this triangle. How do we know? Well, it's a right angle triangle and theta is here. If theta is here, the first thing I always do is draw that line. And that makes that the opposite. This is the hypotenuse because it's facing the 90 degree, and this is the adjacent. So opposite over hypotenuse, sine 5 over 13. So that's what that sine is. How would I find out what theta was if sine theta was 5 over 13? I don't know. Sine theta is 5 over 13. What's theta equal to? I don't know. I'd much prefer if there was just theta on this side, not sine. But if I put in an inverse sine here and an inverse sine here, they'll cancel. So theta is inverse sine 5 over 13. Now, this still looks tricky, but there's no theta in there. There's no x, there's no y. That's just a calculator. So I do 5 over 13 on my calculator and then hit inverse sine. And with that, I get an answer. And the answer turns out to be, well, let's see. Well, it comes up on the next page. I think it's something like 22 degrees or something like that. But we'll see it. But it can be done on the calculator in that way. I'll just see what it is in a minute. I think it's that. Yeah, 22.62 degrees. Okay. So sine theta is 5 over 13. Theta is the inverse sine. So all I did was I put an inverse sine here and I wiped away and left it on this side. If cos was 12 over 13, how was cos 12 over 13? Again, the theta makes this the opposite, makes this the adjacent because this is the hypotenuse. And if cos is adjacent over hypotenuse, it's 12 over 13. So that's how I'd find the theta. And the tan is, I think, 5 over 12. I think it's opposite over adjacent. I can always go back and check. It is opposite over adjacent. I know that that's opposite because I'm interested in theta. So that's opposite over adjacent. And I get my theta that way. So as sine or sheen, inverse sine are related. Each operator is the inverse. So sine of sine inverse, theta is theta. Sine inverse of sine is theta is theta. So they just wipe themselves away, really. And that's very handy for doing questions. The same for cos. You can get rid of an inverse cos with a cos, or get rid of an inverse tan with a tan, or get rid of a tan with an inverse tan. So they all sort of get rid of themselves. It's like if you add +2, -2, they cancel. If you multiply by 2 and divide by 2, they cancel. If you have a cos and inverse cos, they cancel. So now we're asked the question, find the angle theta in this right angle triangle. What is it? So we say there's the angle. It's a 90 degree triangle. This is opposite that, so that's going to be the hypotenuse. But we're really going to start with this one. Theta, draw the line out, that becomes opposite. This becomes the adjacent because it's the only one left. And if we're looking for sine, and we know that sine is opposite over hypotenuse, 5 over 13. But that gives us sine theta. We're looking for theta. So we'll have to get inverse sine of that to get inverse sine of 5 over 13. They'll cancel. So I'll just left with theta. And inverse sine, that's a calculator. 5 over 13, hit the inverse button, I get 22 degrees. And that looks around right. So that's our answer for that. So that's how we solve for theta in that way. Similarly, if they wanted to find cos of theta, we'd do the same. We'd go opposite, hypotenuse, adjacent. For cos, we'd go adjacent over hypotenuse, because that's what the cos is. Adjacent over hypotenuse, 12 over 13. We do the same. We get rid of it with the inverse cos. That would get rid of that. Leave the inverse cos there. 12 over 13 on your calculator. Inverse cos, same angle. So you can see here with sine, cos, and tan of that, we can get the angle this way, and the angles turn out to be the same every time. So that's how we solve these questions. And that's the end of that inverse section. Is that okay? Now, we're turning now to a nice part where we're really doing some of the questions that come up. We've learned all our tricks. We have our toolkit ready, and there's going to be a right angle triangle question on the paper. There always is. There's often many of them. So what happens here is that every triangle has 3 angles, and every triangle has 3 sides. They're not going to give you the 3 sides or the 3 angles in the exam, really. They need you to find some of them. So they'll give you some of them, and you have to find the rest. And it's always a puzzle, just moving it around until you find all the angles and all the sides. So let's look at a standard question. Well, firstly, the right angle triangle. There are 2 types of questions on the paper, right angles and non-right angles. So this is only for the right angled ones. ones. Three and tons run ilmaka. Each lettered side is opposite the same lettered angle. Important that C opposite C, B, B, and A opposite A. The hypotenuse is opposite the 90 degrees. So we're sorted. We're doing questions now on right angle triangles. What are our tools? Well, the toolboxes we have for right angle triangles are the first one that all three angles must equal to 180. And that's always the case. But there's a special rule for right angle triangles, Theorem Pythagoras, Pythagoras' theorem. And this only applies to right angle triangles. It won't apply later. But basically the hypotenuse squared is the square of the other two sides. So if we take the length of this one here, the tevagon, the hypotenuse, and square it, it's equal to the sum of the other two squares, the adjacent and the opposite, or the congruent and the or choric. Okay, so that's the way it works. So the sum of this, the sum of these two squares is the same as that, and that only applies to right angle triangles. Here's a typical structure of a question. What they do is you'll be given certain values for the triangle and calculate the remaining elements. So I've imagined it here like a grid with three angles for the triangle and three sides with the lengths there showing the absolute value, okay, Darvlook, or that length. And the same here for the three angles and the three sides, okay, the three lengths. And they'll start by, say, giving you the length of B, the length of C, so you'll have those two ticks. You might know it's a right angle triangle, that's great. So you have three things, but you don't know the other three. And your job is to tick them all off so you get them all right. So that's the job. The job is to solve these problems. So we're going to start. And the first one is an example with two sides. And I might give you a minute on this just to give you a trial on this. But basically, imagine a right angle triangle with the following sides. You've got B is 8. So this side is known. C is 10. This side is known. You know the 10 there. But this side is unknown. And your job is to find, given a right angle triangle, find A. Find the length of that. So how would you do that? So give that a minute and see if you can get an answer for side A. What is the answer to the length of A? Okay, hopefully you gave that a shot, and some of you might have spotted it and others not yet. But let's go back to the toolbox. The toolbox says, well, this is all I've got in my toolkit. The three angles must add to 180. Well, I don't know any of the angles, so that's not going to be very helpful. Pythagoras' theorem says that the hypotenuse squared must be equal to the other two sides squared. That might be useful. So that's saying is that this side, the hypotenuse, squared, so 10 squared must be equal to the other side squared, A squared plus B squared. But B squared, I know B, so 10 squared is A squared plus 8 squared. That looks promising because there's really only one variable there. One thing I don't know. So that looks like an equation I think I could solve. So let's see how that would work. It says Pythagoras says C squared is A squared plus B squared. So this side is this side plus this side squared. 10 squared is A squared plus 8 squared. 100 is A squared plus 64. I don't like the 64 on this side. I think I'll take it over or something. Or I don't like the A squared on this side. So I'm just solving that question really. 100 is a squared plus 64. I'd much prefer to have a on this side. So I could say that a squared plus 64 is 100. That's one way of getting it on the left-hand side. Now, if I don't like the 64 on this side, I say I don't like pluses here. I'm going to make a 64 here and get rid of it. So a squared is equal to 100 minus 64, which is 36. I don't like a square. Really don't like that square thing. How do I get rid of a square? Well, the opposite of a square is the square root. That would just give me a is equal to 6. Well, I could say plus or minus 6, but because I'm only looking at the positive value, and it's a length, and length can't be minus. The direction can be plus or minus, but the length itself can't be minus. That turns out to be 6. So it looks like a is 6. So we managed to do that question. It was a right angle triangle by using Pythagoras. Example 2. Two sides, find angle A. This is another one of the standard questions that the department can ask you. Every single type of question that they have in their syllabus and in their set of all the learnings you're meant to do, we've taken an example on each one of them. So let's look at A, B, and how we solve here. Given that it's a right angle triangle, we're told that A is 6. So this time we know that. We know that B is 8. Find the angle A. Now that's trickier. To find the angle A from the two sides, but we know it's a 90-degree angle, which is good. You want to give that a minute and see how you do that one, and then we'll solve it. Okay, so let's look at the way we might solve that. We're looking for the angle A, but we've got two sides. So let's look at our toolkit. Our toolkit says the three angles must equal to 180, and you say, that's not going to help me. I don't know the other two angles. Pythagoras' theorem tells me about the three sides. That might help, but it won't tell me the angle A. So I don't know what to do there. I could use it and it might help a bit and try something else later. But the other toolbox I have is sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. Well, if I look at this angle A now, that's the opposite. I always go from the angle to the other side. Because this is 90 degrees, this must be the hypotenuse. And given that there's only one left, this must be the adjacent. So that's the Eochagaín, the Pythagoras, and the congruence. So I got the three of them, right? The opposite, the hypotenuse, and the adjacent. But I know the opposite, and I know the adjacent. So I know the opposite is 6, and the other is 8. So if I go back here, opposite and hypotenuse, I don't know the hypotenuse. Adjacent and hypotenuse, don't know the hypotenuse. But opposite and adjacent, I know this one. I know the opposite is 6, and I know the adjacent is 8. So I know that the opposite over adjacent, which is tan of A is opposite over adjacent is 6 over 8. So that might help us. So tan of A is opposite over adjacent. Tan of A is 6 over 8 is 0.75. But that's not what the question was looking for. The question said, find A, not tan A. But if I know tan A, I can get A, because I can get rid of that tan. That tan A I can lose. So what I have now is, I'm nearly there. I found that tan A is equal to 0.75. I'm looking for A. I don't like anything on the left-hand side except the answer. So I'm going to put in inverse tan here, and I'm going to put in inverse tan here. And they're all going to cancel. That's why I put it in. It looks ugly, but I did it to get rid of it. So A is equal to inverse tan 0.75. Now, this looks a bit tricky, but there's no A's in here. There's no X's or Y's. That's just a calculator, 0.75, inverse tan, and I get my answer. And from that, I find that the inverse tan of that is 36.87 degrees. So that's how I did that, finding it from the right angle. That's example 2. Now, example 3, 2 sides, find angle B. They haven't put it in our favorite spot down here. They put the angle up here, and I've got to figure that one out. And they've told me on this occasion that A is this one, C is this one. Find B. So give that a minute and see how you get on. Okay, this is the way I might try it. I'd say I'm interested in the angle B. So the first thing I'll do is I'll look where B is, and I'll draw a big line opposite and call this the opposite. Across from the 90 degree, the dronilla, I've got the hypotenuse, the tavagon. And if the hypotenuse and the opposite are gone, well, I've only left with the adjacent, the congruent. So that's all I've left. I've got the 3. Now, which of those do I know? I know the adjacent and the hypotenuse. Adjacent and hypotenuse. I know the adjacent is 6 and hypotenuse is 10. So I start looking for something that has adjacent and hypotenuse in it. Not the sine, not the tan, but the cos. Adjacent and hypotenuse. So the cos. So in this case, I can say that cos or cosine B, cos B, is equal to the adjacent, which is here 6 over 10. So not bad. I find that cos B is adjacent over hypotenuse is this. But I'm not really interested in cos B. I'm interested in B. And how do I get rid of cos B? Well, I just magic it away, really, with the inverse cos. Inverse cos. B is equal to inverse cos 0.6. Again, that's not very pretty, but it's just a number in a calculator. Inverse cos, and I get my answer of 53.13. So that's 53.13. And that's the end of the cos B question there. So example 4, this is another question that is on the syllabus and they can ask. And they say, you've got a right angle triangle and you're told that A is 36.87. Find B. So in this case, you're told this is 90, this is 36. What's this one? The angle. So you're told One angle, the 90. What's the one in the middle that's missing? Well, we go through it and we say, I don't think it's Pythagoras, but all three angles must equal 180. So we can say for sure that A plus C plus B, or A plus B plus C, must equal 180. So A plus B plus C is 180. B would be, if we left the others, 180 minus A minus C. A we know because we were given that. So 180 minus this minus that, and B turns out to be 53.13. Because if we know this and we know this, and they have to add up to 180, that must make up the difference. And that's the end of that. That's the third angle. This is a slight variation that they can give just for fun. Here is a right angle triangle, and they say, we're going to give you A, we're going to give you sine B, and we're going to tell you that this is 90 degrees. Can you figure out the rest? So really it's a bit trickier. They don't give you an angle here, but they give you sine B. But if they tell you that sine B is equal to 0.8, we know we can get B, because all we have to do there is get the inverse sine of that. So that's one way of doing it. If sine B is 0.8, inverse sine is inverse sine, B is 53.13. 53.13. And when we know that angle and this number is 90, we can get the other angle, so we have all of those. And there's other ways we can do it then to get the remaining lengths if we want to in other questions going forward. So that's how we find the other angle. So that's how we did it. Was there another way of doing it? That's how we found the angle, all right. Just bear with me. Now, here's a right angle triangle with A, sine B. Find C. They want us to find the length of C. How do we get the hypotenuse for C if we're only given this number 6? So we don't have the hypotenuse value. We don't have the other angles. If we were looking at B, and this was the opposite, and this was the adjacent, we're sort of a bit stuck. How do we do that? So let's just draw it on a cleaner piece of paper and see, because this is the last one in the right angle triangle. Have we a way of solving this? So I think the question I said is, this is 6, that's 90 degrees. Let's say we know that angle is 53.13, because it's not hard if we know what sine B is to get B. We can work out this angle if we need it. It happens to be whatever, but this is the angle of interest. So that's the angle B. If that's the angle of interest and that's the arrow, this would be opposite. This would be hypotenuse, and this would be adjacent. But we're looking for what is the length of C, because we only have this side here. Is there any way of doing that? So I'll leave that with you for a minute, and then we'll come back and I'll go through the answer. So try that for a minute and see, is there a way you could figure out how you could solve that? We're looking for hypotenuse. We know the adjacent. We also know maybe that angle there, which is useful, or we know this angle here we could get as well if we wanted it, because we have 36.87. So we have that angle as well if we want. But opposite, adjacent hypotenuse and this angle, we want to see if we can solve it in some way. We'd love to get the length of that line. Okay, let's think about it for a moment. Adjacent and hypotenuse are sort of interest to us because we want to get the hypotenuse and we have the adjacent. So do they ever show up anywhere together, adjacent and hypotenuse? I think they did somewhere. Adjacent and hypotenuse came up with cos. So cos has something to do with adjacent and hypotenuse, which is good. So it looks like cos B would be adjacent over hypotenuse. Cos B, and adjacent we know is 6, and hypotenuse we don't know. We're going to call that C on the bottom because we don't know the length. We do know the angle B, so we're now saying that cos of 53.13 must be equal to 6 over C. Not great, but there's only one thing we don't know in the whole lot. So we should be able to solve it. So let's see how it works out. What we're doing here is we found the angle B was 53.13. And then we said A is 6, B was this, C was 90 degree. And if we looked at it this way, cos was basically the adjacent over the hypotenuse. Adjacent over hypotenuse was 6 over C. So cos of that was 0.6. So 0.6 was equal to 6 over C. Now that's just an equation, so hopefully we can solve that. That's just algebra really. We're left with 6 over C is equal to 0.6. How would I solve that? Well, the way I'd solve that is I really don't like C on the bottom. So I'd put C on the top and C on the top, and they'd cancel. So 6 is equal to 0.6 times C. I really don't like multiplying by 0.6, so I'm going to divide by 0.6 and divide by 0.6. And then I'll get 10 equals C. I much prefer C on the left-hand side, so I'll say C is equal to 10. So I found the length of that side. So I went around, a little bit around, but I knew the angle. I had one of the sides. I knew it was 90 degree, so I could find out the one I was missing. Adjacent and hypotenuse made sense because I had adjacent. I needed hypotenuse. That's why I chose the cos, and that's how I found that that length was 10. So really, that's the end of the right angle triangle. So just go back through it again. A typical scenario, they'll give you two sides and a right angle, or two sides and find the rest, or an angle and find the rest, or whatever. So if you're stuck and you know two of the sides, you can use Pythagoras, because that's one of the good handy tools to get in there. If you know two of the sides, you could use the sine, cos, or tan to get the angle. Because if you know that this is 5 and this is 12, and that's a right angle, you should be able to get that, because that's opposite. That's whatever that would be, adjacent. Opposite over adjacent is tan. So tan of theta is 5 over 12. 5 over 12 is a number. You can get the inverse tan of it, you can find theta. So that's how you'd find the angles. You could use, once you found one angle and you know the other is 90, you can get the third angle. So you have it. And the only trick is sometimes they won't tell you the angle. They might say, they won't tell you the angle is 30, but they might say the sine of the angle is 0.5 or something. And then you have to convert it back. And that's it. So that's the full set of questions that are allowed under the syllabus on right angle triangles. So you just remember those tricks, use them as you wish, and you've fully covered right angle triangles. So we just take a minute then and just catch your breath, and we'll start on all other triangles. They're the ones that don't have a right angle in them. Okay? Just take a minute and we'll start again in a sec. Okay, so Okay, thank you for that. So, what have we done? We've looked at the trigonometric functions, the sin, cos, and tan, the sine, cos, and tan. We've solved every question that can come up on right angle triangles. And I'll look at some exam questions in a minute. And you just see how we fit these bits one after the other. But the next one then is we're going to look at triangles that aren't right angle triangles. It'll be very easy in the exam to see this. If you see a triangle and it looks like this, you know, you'll be told if it's a right angle. If it's a right angle, there'll be a piece there and it'll say PQR is a right angle triangle. If they don't tell you that and it's something like that, you say, assume it's not a right angle triangle unless they tell you. Okay? So this is all triangles, sine and cosine rules. So these are oblique triangles, all the angles different, all the sides different. Again, the only thing that stays. Angle B, opposite side B. Angle C, opposite side C. Angle A, opposite side A. Really, that has to be right. Otherwise, all the equations will not work. So, we've left Pythagoras behind. We can't use it really. We're looking at what toolboxes we use now for not angles that are not, triangles that are not right angled. So here's our new set of toolboxes. We marked these as special toolboxes for us. This is our set. What have we got? We've got a rule here that says A plus B plus C is 180. All angles add up to 180, and that's great. Then we've got a cosine rule, real and cohenous, and we have two versions of it. A squared is B squared plus C squared minus 2BC cos A, or cos A is B squared plus C squared minus A squared over 2BC. That's actually the same equation. It's just turned around a little bit on its head. And just to show you that for the fun, as a bit of distraction, so we get used to doing this in calculations anyway, let's say that A squared equals B squared plus C squared minus 2BC cos A. And let's imagine that in the exam, they say, find cos A. This is very standard for leaving cert questions. For example, in a question about a sphere, people might say, oh, something, the volume is 4 over 3 pi r cubed. They'll never say, if r is 10, find v, because it's too easy. What they'll say is, v is 100, find r. What's r? And really what we have to get good at is taking the letter they're interested in and putting it over on the left-hand side on its own. And then everything else works out. So I'll do that one in a minute, but let's do this one first. Here I'm looking at cos A. How do I put cos A on the left-hand side and get rid of everything else? Well, the first thing I'm going to do is I'm going to do it this way. I'm going to say B squared plus C squared minus 2BC cos A is equal to A squared. I've just turned that around. I said if A squared is this, this must be A squared. So at least cos A is on the left-hand side. It's not very pretty, but it's on the left-hand side. The B squared is a plus, so I'm going to get rid of it with a minus B squared. And the C squared I'm going to get rid of as well. So now I'm left with minus 2BC cos A is equal to A squared minus B squared minus C squared. I really don't like that minus. It's minus times something. It's a multiplier of a minus. It's multiplying everything by minus. So I'm going to get rid of it by multiplying it again by minus. So I'm going to turn that, multiply everything by minus. So I'm going to say minus into all of this and get rid of it. So I'm going to get 2BC cos A is equal to, that's going to be minus A squared plus B squared plus C squared, or B squared plus C squared minus A squared. And that's okay, but if you think about it, I was interested in cos A. So I just want this bit. And if I just want this bit, this is a multiplier. So I'm going to divide by that. So I end up with cos A is equal to b squared plus c squared minus a squared over 2bc. Now, we don't have to learn that off, but that's what the answer is. B squared plus c squared minus a squared over 2bc. So the first equation is the second equation. It's exactly the same. It's identical. So that's how that would work. And sorry, I did say that I introduced that one in the sphere. So let's just finish that so that it's not leaving it loose. V is equal to 4 over 3 pi r cubed. Let's say the examiner was only interested in r. What's r equal to? Well, the first thing you'd say is, I don't like that 3 on the bottom. I'm going to multiply by 3 on the top, because that will help a bit. So I get 3v is equal to 4 pi r cubed. I don't like the 4. It's a multiplier. In fact, I don't like the 4 pi. That's just a multiplier. So I'm going to go 3v over 4 pi is equal to r cubed, or r cubed is equal to 3v over 4 pi. That's looking a lot neater, but I'm really only interested in r. How do I get rid of a cube? I take the cubic root. And now I get r is equal to the cubic root of 3v over 4 pi. Now that isn't pretty, but the examiner will have told you what v is, maybe 100 or 1,000 or whatever. It's a number. 3 times a number divided by a number, the cubic root, you have your answer. So that's really the way we do equations, and we can turn everything around. So back to 3 and Tánacht. And back to non-right angle triangles. So that's a rule we can use, the 3 angles. The cosine rule comes in 2 forms. And the sine rule is a very useful rule that says a over sine A, b over sine B, and c over sine C are the same. So the length of the side A over the sine A and the length of B and the length of C are the same. So that's important. So they're positive values there. And that's the same. Now, the cosine rule is fairly handy. It says if you have everything on the right-hand side, then you'll get the left-hand side. So in this case, if you've got the length of 2 sides, B and C, and the angle between them, because the angle A will be between these 2 sides, then you use this one. On this occasion, if you've got the 3 sides and you're looking for an angle, you get it this way. So the cosine rule will find you an angle or a side as long as you have the other 2 sides and the angle between. The sine rule, if you have a side and an angle and one of the others, it will help you. So a side and an angle, and maybe a side and looking for this, or an angle and looking for this, or this looking for this, or this looking for that. As long as you've got, each of those is its own set. So that's a set of just of 4 together. As long as you've got 3 out of the 4, any 3 out of the 4, you can find the other one. So there's our toolboxes. We're going to use that. We're going to bring it with us anytime we're doing a question on triangles that are not right angle triangles. So that's our toolbox. How do these questions work? Well, the way it'll work is that there'll be 3 angles and 3 sides, and they'll tell you some of it, maybe an angle and 2 sides or something. Note that it's no longer 90 degrees. We don't have a 90. And we're going to try and turn it into something that we know it all. Okay, we've got all the sides and all the angles. So that's our job. We're going to follow it around like a game of Sudoku or filling in the last bits of the jigsaw. So what types of questions are they allowed to ask? Well, there's only a set number anyway, and they ask them all. So this is what the government has on your list, on your formal step-by-step list. Given a triangle with the following values, A is this, B is this, and C is this, find A. Angle. So find A. A is this, known. B is known. C is known. Find A. So give that a go for a minute and see if you can find which of the toolboxes tools you're going to use to solve that question there. Okay, let's give it a go. Well, it says find an angle here. So if we're looking for an angle, we say, oh, we can find an angle if we know the other two angles. And we don't. We can find the length of a line, not interested really. We can find the cost of an angle. Well, that's not bad. If we had the cost, we could probably find the angle. We can find the cost of an angle if we know the length of the other three sides. Hey, we know the lengths of the three sides, which is great. So I think we can use the cosine rule, real and cohenish pyramidal. The second form of it here, cos A is this. Okay, so let's go with that. Cos A is, what does the formula say? Well, now we just transcribe it. Cos A, b squared plus c squared minus a squared over 2bc. Cos A, we're looking for A, so A must be here. So we don't confuse it. That's A, 5.814. So really we should probably write down A is 5.814, B is 7, and C is 8. Okay. So now, cos A, directly from the tables. And then we go back to what our equations were. We had A is this, so that's our A. Our B is our 7. So B squared is 7 squared, C squared is 8 squared, A squared is 5.81 squared over 2BC. So we write that down, and then we take a bit of breath, and we say that's just calculator. So that 4964, add them all up, divided by whatever, and we get cos A is 0.7071. So, but we didn't want cos A, we wanted A. So if cos A is 0.7071, to get A, we just take the inverse cos. A is equal to inverse cos, that 45 degrees. So that's how we do that. And that's how we get the angle. So that's example 1, 3 sides, find the angle. Example 2, 2 sides and you have a shared angle. So here you've got the angle A, which is great, the side B, which is great, and the side C. So we've got 2 sides and the angle in between, which is great. So we've got the 2 sides, B and C, and the angle A. We're trying to fill the other gaps. Okay? So which one do we use for that? So do you want a minute again on the rules? Which one would you pick? So we're looking for 2 sides and the angle in the middle. Now, well, I don't think we'll go with the angles A plus B plus C because we're really looking at the length here. The side says A squared is the other 2 sides with the angle in the middle. It looks like cosine rule 1 is going to work. So that's great. Cosine rule 1 is going to work. So I'm going to use that. Cosine rule 1 is A squared is B squared plus C squared minus 2BC cos A. So what are the rules again? Well, A, I don't know. That's the piece I'm looking for. B, I know is 7. C, I know is 8. and cos A is 45 degrees. So I just plug in the numbers. B squared is 7 squared, 8 squared, all the numbers there. Cos 45 is that. A squared is 33.8. A is 5.814. So that's that page done. Now you have 3 sides and 1 angle. Now, the next example, 2 sides and an opposite angle. Here you're told that the angle is 45. The side is A and the other side is here C. So you're told this side and this side, but you don't have the angle in the middle. That's one side, and the other side you don't have the one, but you have an angle over here. So you now say, which one are you going to use for that? So have another minute and see which one you'd pick. So we're looking for the angle C. Well, the angle C, we know one angle. So can we use the angle rule? Well, we don't know the other two, so that's a no-no. This angle here, on the cosine rule, if we know the 3 sides, we have one side, we have two, we don't have the third side. So we can't use that. The sine rule is the only one left, so hopefully it will work. A over sine A, B over sine B, C over sine C. Well, what do we know? It looks like we know C. We don't know sine C because we don't know C. B, we know, but we don't know sine B. But A, we know, and while we don't know sine A, we know the angle A, and we should be able to get sine A. So it looks like that's our key. A and sine A we sort of have, because we have A. So let's look at the angle A. A over sine A, it looks like we've got most of that. And we're looking for the angle C, so we're interested in that. And I think we have the angle, we're looking for the angle C. We're looking for that angle there. So we're looking for this one. We have that. We're looking for those two, A and the length A and that angle A, the angle C and that. We know nothing about B and we're leaving them out. So A over sine A, that's A, 5.814 over this, is the same as C over sine C. So give that a try for a minute. So A over sine A, that's A, 5.814, over sine A is sine 45, is 8 over sine C. I don't know what sine C is. It's just one of those missing things yet. But there's 4 parts to that, and I know 3 of them. So I should be able to solve it. Sine 45 is also that number there, so I should be able to use that as well. So 5 over sine C is just 8 over that. So I'm just plugging in the numbers. That's that over sine C. So 8.22, whatever 23, is equal to 8 over sine C. I want sine C. I prefer sine C to be on the top and on the left-hand side. So I'm going to multiply it here by sine C to get rid of it from the bottom. And therefore I have to multiply here as well. And that cancels that. So now I get sine C times 8.2223 is equal to 8. Really don't like this multiplier here, so I'm going to divide by that. And divide by it here too. So sine C is equal to 8 over 8.2223. This is just a calculator, whatever that number turns out to be, I don't mind. I think it's sine C is equal to 0.97296. But again, I don't want sine C. I'm interested in C. So how do I get rid of a sine? I look at it and I say, if sine C is that, I'm going to put in, if sine C is equal to 0.97296, I just put in an inverse sign in front, and I get C is equal to inverse sine 0.97296. That might be messy, but it's on a calculator. There's no values in, there's no variables in there. I just stick in 0.97296, hit the inverse sign, and I get my answer. And I find that the answer after all of that is that. C is equal to 76.64. So that's how I did that. And that's the end of that. So the approach to questions that are not right angle triangles are, you've got given some bits and you have to find the others or whatever. If you're given two angles and you're looking for the third, you use the 180 rule. If you're here and you're given two sides and the angle in between, you use the cosine rule. If you're given the cosine rule and you're given the three sides but no angle, you can use it to get one of the angles because you know all the sides. If you're given two of the angles and one of the sides and they're matching, you can use the sine rule. Or if you're given, say, two of the sides and one of the matching angles, you can use the sine rule. Either way, you can get around the houses. It's all done. So that's the end of that topic. It's a long topic. There's always questions on it. It's always nice to solve, but there are the tricks. Okay? So a little bit more before we finish, and then we do some exam questions. We're now onto this topic called the area of triangles. It's just a few equations. Sometimes it goes up in the line question, sometimes in others, but let's just do it here now. Here's a formula page. So it's another toolbox trick that you bring. And it says the area of a triangle is half one side by the other by the sine of the angle in between. So if you use AB as the sides, it's sine C. BC as the sides, it's sine A. And AC as the sides, it's sine B. Or another way of doing it is half the base by the perpendicular height. So we'll keep that as a way of measuring the areas of triangles. Here's an example of a triangle. The length is 12.81 this way. The length this say is 10 plus 2. So the full length is 12 from the beginning to the end. And if somebody says, what's the area of the triangle? Well, you know this length is 12. You know this length is 12.81. You know the angle in between. So the answer is half times 12, one length, by the other length, by the sine of the angle in between, and that's 48. If you were doing this the other way and you were told this was a right angle triangle at this amount here, and this was 10, and this was 12.81, and you were told this angle here, so you knew this was 10 and this was that angle, and this was the opposite, and this was the adjacent, and this was the hypotenuse. Working it all out, you could find this particular length and height as well. So let's imagine that you find that that particular height is I think it's 8 or something like that. But you can do it because you know the adjacent and the hypotenuse, so you can find out, if you know the adjacent and the hypotenuse, you know the cosine. So cosine of that, whatever that is, and then you can work out then what this length is here. Is that okay? So you've got all the various lengths. Or you could do it by Pythagoras. You could say 10 squared plus this squared is whatever. So you can work that out too. So there's loads of ways of getting that length. But if you did want to do it, then you say it's 12 plus the height. So that's the other way of getting the actual height. So the base by the perpendicular height, it's half by the base by 8 is 48. So that's ways in which you can solve that. Now here's an exam type question, and I'll go through more in a minute. But here's an exam question where they say sectors of circles. Remember that a circle it's not really triangles, but a circle has a number of formulae to it. I'm marking these as a keynote for you. It's in your toolbox, but it's also on the log table, so you don't have to remember it. The perimeter, imline, the outer circle, the length of it is 2 pi r, 2 times pi times the radius. And the area is pi r squared, or pi r carna for the ochre. Okay, so you've got the area, you've got the square measure, and the other you've got the length. Now, if you don't go around the full circle, and let's say this was only the angle A, the length you're going around is only a certain amount. Now, in a full circle, you've actually got 360 degrees. So A over 360 would be the fraction of the circle that's in green there. So 2 pi r times A over 360, that fraction, would tell us that's the length of that piece. And 2A over 360 by pi r squared would tell us the area of that piece. So for example, if A was 90, a 90 degree there, then it would be a quarter of 360, and that would be about a quarter of the, and it probably roughly is a quarter there. Is that okay? So that's a quarter of the circle and a quarter of the length of the perimeter. Okay, so we'll keep those as useful equations. Or there they are again, just the length of the arc, the length of the perimeter. So that's really our formula page. Is that okay? Again, it's in the maths tables, you can look it up. So here's an example of a question. Find the size of the shaded area in red. So that's a former exam question. It's a circle, really. This bit here is like an ice cream cone that, well, it's a bit flat, but it's an ice cream cone. It's a sort of a sector. It's got a red bit and a green bit. And all of it is like a cutout of a circle. But the green bit alone is a triangle. And they just want us to find out what's that bit there. So how do we do that? Well, we might do that by actually trying to find out how much is actually, I think, we'll try to find out how much is in the overall sector and then in the green bit. So let's look at the area shaded red first. Well, let's look at the red and green together. The area of a circle is pi r squared, but the bit we have is only 90 degrees of it. So we're only getting 90 out of 360, or a quarter of the whole circle. So a quarter of the circle is pi r squared over 4, because it's a quarter of the circle. Is that okay? Now, just waiting for that. I think it's just causing a little bit of interference on that. I'll stop the camera for a moment and just see. Now, it's still finding those lines tricky, I'm afraid. Okay, so it might be easier somewhere else. Okay, now, so what we're trying to do now is with this, we're going to try and get the area of the triangle in the middle. Well, the triangle in the middle is just the green bit. And what I'll do now is I'll just maybe do it here. It's just those lines are just a little bit close, and it's causing the camera to do a little bit of a jump on me there. So that's the area of the triangle. So that's 20, 20, and this bit on the top is the actual sector. Okay, we know that's 90 degree. So that's the circle. It continues all the way around. So how much have we got in just this little bit here? Well, this little bit here is a triangle. And I think we have an equation for the triangle. Where was it? I think we had it somewhere. The area of a triangle was half AB times sine C, or half the base by the perpendicular height. Well, it's half, if that's A and that's B and that's the angle C, it's a half times 20 times 20 times sine of that angle C. But actually the angle is 90 degrees and sine of 90 is 1. So it's a half of 20 times 20. Or another way of looking at it is it's a half of the base by the perpendicular height, because it's a 90-degree angle. So that's how that works there as well. So it's half of 20 by 20. And 20 by 20 is 400, and half of that is 200. So that's the area of the green bit. What was the area of the total sector? Well, the total sector was a quarter of the circle, which was pi r squared over 4. And the r was 20. So pi 20 times squared over 4 is that. So that's the area of the red bit, minus the bit in the middle is actually the area of the green only. The bit in the middle is that. So that's how you would do that question. And that's how that was done. The very last bit on the trigonometry is just something that they put in about compass directions. We probably don't think about it really, that we're so used to X and Y and all the work done by they call it the Descartes, the Cartesian system, or, we're so used to the squared system that, like, we're used to going out for X and up for Y, that we think nothing about this point being 1, 2, 3, 4, 1, 2, 3. So this point here of 4, 3, we're so used to doing that. We think of doing X first and then Y. It's everything that we do, X and Y. Always think horizontal before we go vertical. It's almost like the way we read horizontally before vertically, though we go down the page, not up the page. But you get the idea. We're so used to that system that we forget to think there's another one. But there is another one, and it's older than that. And it's to do with compass directions. When we talk about compasses, we have north, south, east, and west. And they're sort of like our directions here as well, of north, south, east, and west in that particular way. We're used to having them in that way, where we've got sort of east here and west and north and south. But if we were asking you to get to that point there, we would say 1, 2, 3, 4, 1, 2, 3. But we would never say east, north. We always say northeast, not east, north. We never say west, south. We always say southwest. So the way it works in the compass system is that we always call the vertical first. So we talk about this being north, south, and then east, west. So the wind was from the southwest or from the northeast. We never say east, north. It just doesn't ring right. So this point here, or this direction here, at 45 degrees is 3, 3 this way. We would call that north, 45 east. So we go north first and then turn towards east, or north and turn towards west. But we never go west or east first. And the same here for south. We say south, so much west. So that's south, 63.44 west. And it's just a way of remembering. We always use north and south before east and west. Finally, these are just special angles of 30 and 45 and 60. That when they started off doing angles, well, if this was the same length as this, very useful for tiling or whatever, way back the Grecians working out various bits of land or whatever, 1 and 1. Well, 1 and 1, because of Pythagoras, 1 squared plus 1 squared is 2. And this becomes the square root of 2 in terms of its length. So that becomes a 45-degree angle. If those two are the same, the angles must be the same. If that's a 90 degree, there's only 90 left, split, 2 45s, and that's it. Now, the next one then is, so sine of 45, if that's our 45, is our opposite over hypotenuse. So it's 1 over root 2. Cos of 45 is adjacent over the hypotenuse, and tan is opposite over adjacent, which is 1. So that's our 45-degree angle. We look at our 60-degree angle, where they're all the same. The trianton cotlassoc, they're all the same, where we've got the three sides identical, 2, 2, and 2, 60, 60, 60. We could split them into 1 and 1. So that would be a 90 degree. And then 1 squared plus something squared is 2 squared. Well, 2 squared is 4. So 1 from 4 is 3. The square root of 3 is the square root of 3 there. So that must be the square there for that to be right. So the three sides of a 60-degree angle are root 3, 1, and 2. So if we look at that for the sine of it, and that's the opposite, that must be opposite, adjacent, hypotenuse. Opposite over adjacent, hypotenuse is root 3 over 2 for the sine. Cos is adjacent, it's 1 over 2, and tan is root 3 over 1. And if we didn't want the 60 degree, and this was 90, we can get the 30 degree. So to get the 30 degree angle, we would start here, call this the opposite, this the adjacent, this the hypotenuse, and then say sine of 30 would be opposite over hypotenuse, 1 over 2. Cos would be adjacent over hypotenuse, or congruc or tevagon, and then tan would be opposite over adjacent, or coric or congruc, and you get it that way, opposite over adjacent. And that's the end of that. So that's the full set of questions on trigonometry. But before I go, I'd just like to just work through an exam question, not at all, but just to show you how the steps sort of find their way in and do that. So I'm going to pull up an exam question now just for a sec. Okay, bear with me. This was an exam question from 2019. And you can see it here. It'll be on your notes later. You can draw it down over the next few days, or you'll have it anyway from the exams, the State Exams Commission papers as well. You'll also have done it most likely. But there's the question, and it's a radar system sending out radars, and a ship is going along here and cutting into the radar here and here, and then leaving the radar. And the question really is, how do you solve this question? Now, they've given you some clues. So they started off by saying, here is a clue we've given you, that's 120. This is a right angle triangle because it's the shortest distance to a straight line. And they told you that. This is the angle 30 degrees. They say, okay, if that's the case, can you find this length here? And you say, I don't know. But then you look at all the things we've done already and you say, can I solve that question? Well, if I had a triangle and I turned it around properly, and let's say I had a triangle like this with the right angle, and I knew that, what did I know? Let's see what I know. I know that the hypotenuse is 120. I know that that's a right angle. I know that this is 30. Can I find this angle here? Well, I think we could. We could say that is the opposite. That's the hypotenuse. We know that the sine is that over that, and we know the angle is this, and we know that sine 30 is a half. So I think we can find that that angle is 60. So that gives us this one here. And then it says, what else can you know? Well, can you find this length here? Well, you can, because it's the radius of a circle. And this is the radius to the circle, and that's 100 kilometers. So this must be 100 kilometers. So that's 100, that's 60. If that's 100 and that's 60, can we find this angle here? Or that length here? I think we can, because we know two of the sides. Pythagoras will give us the third. So now we know the length of that. And the last bit of the question was, having done all of that, you've done all that, you now have, they're now looking for this length here, because we don't know that length, SQ. But we do know that this is 60, and we do know that this is 100, and we know that this is 100. So we can forget the thing in the middle, okay? We also know that this is 30, and we know that this is 30. Oh, sorry, we didn't know that was 30. So we know that. Is there any way we can find this length? Well, we have, sorry, I'll do that again. We've this length here and we've this length here. So we can find that length because we know from Pythagoras that that's 60, that's 100, we can find that. So we know that length. So now we end up with this triangle where we know this length is 100, this length is 100, and we know this length as well. Can we find that angle? Well, if we know 3 lengths of a triangle and we're looking for the angle, we can use the cosine rule. So that's the way all of these things work. It's like Sudoku, one step, one step, one step. So I absolutely guarantee you that the steps that we've learned in the tricks, there aren't any more tricks. They're all covered in those steps. And you've got to say which one works, move the next bit of the Sudoku on, and you're done. So once again, apologies, I've gone over by a few minutes, and we'll take it off the next. So if we could see you again at 4 o'clock. This is Tomás signing off here in the background there from the campus in Griffith College, Cork on Wellington Road. And I'll join you from another campus in about half an hour's time. Slán go fóill.